Okay, let's take a look at a couple of examples of reducing rational expressions. Of course, a rational expression is simply a fraction where the numerator is some polynomial, like x squared minus 2x minus 3, and the denominator is also some polynomial. Okay, so this is example number 1 here. If I'm trying to reduce this, what do I do? Well, remember how we reduce fractions of integers. If you were looking at, let's say, 30 over 42, for example, how do you reduce this? Well, one way you could go would be to ask yourself what goes into 30 and 42 both evenly. What's the largest such thing? And then divide top and bottom by that value. But that's a hard question to answer in the context of polynomials. What's the biggest polynomial that goes into both of these? It's probably not something you can solve by inspection. There's a better way, though, for reducing both of these things. If we go back to our fraction of integers here, what if we came up with a prime factorization of 30? Of course, that's just 6 times 5, or 6, of course, being is 2 times 3. So 2 times 3 times 5 on the top. And then 42 is, well, let's see, that's 2 times 3 times 7. As soon as you have the prime factorization, it's very, very clear what this is going to reduce to, because the 2's cancel, the 3's cancel, and what you're left with is the reduced version. Okay, so that's exactly the same process we want to employ to reduce rational expressions. Completely factor the numerator, completely factor the denominator, cancel anything that's common in terms of factors, and what you're left with is the reduced rational expression. Okay, so up top here we have a trinomial. We want to factor that completely. We're going to make a good guess that this is the product of two binomials. We're going to guess that the two first terms are x, so that we get x squared there. We need a product of 3 from the last term, so let's assume a 1 and a 3 there. It's negative, so we know these are different signs. And the inner product term and the outer product term here have to combine together to give us negative 2x. The only way that happens is if that's negative and that's positive. So we have factor at the top. Now looking at the bottom, we want to completely factor it as well. Always check for common denominators, common factors first. There's a 3 here that we can pull out. That leaves x squared minus 1. But notice this is not yet completely factored. In fact, looking at this, we have a difference of the square of x and the square of 1. This is a difference of squares. So I can write this as the sum of x and 1 times the difference of x and 1. Don't forget our 3's coming along for the ride. Don't forget we have an x plus 1 and an x minus 3 up top. Okay. Having now completely factored the numerator into this and completely factored the denominator into this, just like in the example below, anything that's common can be killed off. So the x plus 1 that appears in both of those can be canceled. That leaves only x minus 3 over 3 times the quantity x minus 1. Okay, and so that is the reduced rational expression. If you want, in some cases, it might be useful to multiply that out on the bottom. You could say this is x minus 3 or over 3x minus 3. Other cases, it's going to be more beneficial to leave it in factored form. So really, either one of those two guys is probably fine. I will make one more little note here, though. Do know that this initial expression and this expression on the end are absolutely identical for almost all values of x. All right, if you plug in, let's say, x equals 7 into this, that's going to be equal to this expression where x is 7. You're going to have a 7 plus 1 over 7 plus 1. That's a factor of 8. Those are going to cancel. Everything else is going to play out as being exactly the same. So for most all values of x, this identically equals this. But there is one exception. What if x equals negative 1 here? When x is negative 1 here, notice we have a 0 over a 0. Okay, 0 over 0, that's indeterminate. We couldn't even really cancel it, really. Okay, if I plug in -1 into this expression for x, I end up with 0 over 0. But if I plug in -1 into this expression, I don't get that. In fact, I get, what, -4 over -6, which reduces then some 2. Okay, that's going to be a very, very important detail that's sometimes glossed over, but it becomes very, very important once you get to calculus. Okay, so for now we're going to assume that this expression involves some x that keeps it defined, it keeps it from going indeterminate, and we'll go ahead and use equalities throughout. But don't forget that detail. When x is something that makes this indeterminate, we might have a problem. Right? But for now, again, that's our final answer. All right, let's look at another example. Number 2, 5x cubed minus 10x squared plus 20x, all of that over x to the 4th plus 8x. Okay, so here again, the strategy, factor the numerator completely, factor the denominator completely, cancel whatever's common to both, and what you're left with is the reduced rational expression. So we have to factor this numerator. First thing we look for, of course, is there a common factor? Sure, there's an x on every one of these. There's a 5 as a factor on everything in the numerator. So I can pull out a 5x. That's going to leave, let's see, for this first term, what do I need to multiply 5x by to get 5x cubed? That would be x squared. 5x times something gives us -10x squared. That would be -2x. And 5x times something gives us 20x. That something would have to then be 4. So there's a partial factorization. We may be able to go further than that. On the bottom, here again, we can pull out a common x. That's x times x cubed, right? That product gives us the x to the 4th, plus 8. That product, again, giving us 8x. Okay? So it's very clear, even at this stage, that we have an x over an x. Those two are going to cancel. What's unclear is, can we do anything with this? Okay? The top looks like a trinomial. We could maybe try to factor it into the product of two binomials. But before we do that, look at the bottom. Isn't that instantly recognizable as something that factors? That's a sum of 2 cubes, right? That's x cubed. That's 2 cubed. And we know by the formula for the sum of cubes that we can factor that into x plus 2, right? 2, again, is the thing you cube to get 8. X is the thing that you cube to get x cubed, times x squared minus the product of these two things plus the second guy squared. Looky there. Did we get lucky or did we get lucky? That just happens to be the exact same thing as what we have above. Okay, so that would be like getting a 6 over a 6 here. We know we can cancel the 6's. We don't have to break it down even further to 2 and 3. Cancel that with that, and all we are left with is 5 over x plus 2. Okay, so that's the reduced form for that guy. Again, under the caveat that we're only worried about x values that make this defined. In the cases where this is indeterminate or undefined, some other things may happen here, and these two things may not absolutely agree. But as long as x is chosen so that this is some actual real value, then it will agree with this, and this is the reduced form. Okay? That's it.